Hello and welcome back to Calculus 1. This is section 3.2. We are talking about derivative as a function. We are learning about connections between functions and their derivatives. So each function has its own derivative, right? And we can find that derivative if we crank the limit you guys had on your exam and covered last class. So we know so far that if you do the limit procedure and you find the derivative of x squared, let's say, you will get 2x. Now we did this in class by solving the limit. H goes to 0. Now we have f of x plus h, which is x plus h squared minus f of x, which is x squared divided by h. When we do the limit, we have x squared plus 2xh or hx plus h squared minus x squared divided by h. These guys cancel and we get limit h goes to 0. We can factor out h. We have 2x plus h divided by h. Now these two cancel, and finally we have limit of 2x plus h as h goes to 0. Now we let h go to 0, and the answer is 2x. So that was a proof that the derivative of x squared is 2x. Now we can graph both of these, and we are going to see two different functions, right? So 0, 1, 1, 2 and 4, negative 2 and 4 and 2 and 4, 3 and 9, or maybe higher, whatever. So we have our parabola, and we'll call this f of x. That's the black line. And now I draw 2x, which is a linear line. So it goes through the origin, 0, 0, because the y-intercept is 0, 2x plus 0. And then I go 2 units up, 1 unit over, 2 units up, 1 unit over. I get to draw the line, and that is f prime of x, the derivative. So we see that derivative, well, we know from last time that derivative is a function. And in this case, it's a linear function. We have a quadratic function that is our input, and linear function that is our output. In this case, the derivative. So we can graph both of those on the same coordinate system, but then we have to be careful, right? Because the y-axis is at the same time also y prime axis, depending on which graph you're going to look at. And we also see now that the red function, which is the derivative, is a function because it passes vertical line test, and it's a linear, so we know it's a function. It's a linear line, belongs to polynomials. So we can do this now for other functions as well. With skipping our limit proof and all of this stuff, we did last time the derivative of 1 over x, and we had negative 1 over x squared. Now I can graph both of those on the xy plane. We know that x squared is 1 over x is this, and then the x squared negative 1 over x squared will look like that. So we have our derivative, and our black is the regular function. So when you look at this now, you see one interesting feature, and that is that your 1 over x has the vertical asymptote at x equals 0, and also your derivative has the vertical asymptote at x equal to 0. And you will quickly realize that every time you take the derivative, vertical asymptote gets preserved, the same spot. So if you had the vertical asymptote at 1, the derivative will have vertical asymptote at 1, x equals 1. So when we take the derivative, vertical asymptote is preserved. So it's going to stay at the same location. Eventually, we are going to see that the derivative of ln x is 1 over x. ln x has a vertical asymptote at 0, and 1 over x also has a vertical asymptote at 0. So every time when you take the derivative of a function, the derivative function will have vertical asymptote at the same spot where the other function had it before. And one last part, what is the derivative of a constant? Y. The answer is correct, y. Derivative of a constant is 0. Why? Because it's constant? Let me see what these guys are going to say.
Constant have a slope. There is a 0 slope.
Constant have 0 slope. What do you have? Slope is 0. So we know that the derivative actually measures the slope, and every constant function is going to be graphed as a horizontal line whose slope is 0, so derivative better be 0, right? There is one easier explanation. Can anyone pick up on the easier explanation? What did I say the derivative measures? Okay, what's that second word you said?
Change.
And how much of a change do you have in a constant? 0 change, right? So derivatives measure change. Change of a constant is 0. It's a constant, right? So that's even better way to remember that the derivative of 3 or derivative of 1/2, whatever. If you have a constant, derivative of a constant is 0 because there is no change. So this is going to be one of the formulas that you will be memorizing, obviously. And now if you graph, you will have your function. This is your function f. And then if you go and graph your derivative, the derivative will be equal to 0. So f prime. It's actually x-axis, right? So these are some of the cool things. And the last piece of the puzzle, and then we can put all of this together, is what happens at extreme values such as minimum and maximum. What happens with the derivative at that point? So if you think about it, let's put the function, say, like that, all right? And we see we have a max over here, we have a minimum over here, we have a maximum over here. What is the tangent line at this point? Tangent line measures the slope, right? Which is the slope of the function. So what is happening at these lines? They are horizontal, right? We have a horizontal tangent line. So this is a horizontal tangent line, another horizontal tangent line. So this means that, and I have to write this in blood because it's very important. All min-max points have tangent line with slope 0. This is something that it's very important. And this is one of the things that actually Newton used to explain motion. When you throw something up, what happens when you throw something up?
Stops.
It stops at the maximum height, right? Where does it stop? At the maximum height. So when you throw something, it is going to go up and it's going to get slowed down by gravity, and then it's going to reach the highest point it can. That depends on initial velocity, how hard you throw. And then the gravity is going to beat it and bring it down. That's why you can jump and you go down, right? Athletes jump higher because they practice, right? And exercise and so on. What happens? So every time gravity pulls you down, unless you shoot something at so fast with escape velocity, and if you have escape velocity, it's not coming back because gravity is not going to pull it back, which is why we can launch rockets into space. Right? The propulsion of a rocket is going to give it enough of that velocity to achieve escape velocity, and then there is no coming back, right? It's going to shoot off of the planet. So now we see that every time when we have a min and a max, we have derivative to be 0. So in other words, over here, let's translate using blue. Every time f of x has a min-max, f prime is equal to 0 at that point. So anytime you have, or every time when you have a min or a max, and we're going to come back to this concept many times in chapter 3 and chapter 4, which will include a lot of word problems and a lot of different, at least 2 sections of word problems will depend on this, and then another 2 sections in chapter 4. So we're looking at least around 4 or 5 sections that will be based just on what I wrote in this, in your view right now. So make sure you understand this and make sense out of it. Now, what we are interested at here in this lecture is the relationship between the derivative, the function and its derivative, because derivative is also a function. So is there some kind of relationship that it's always there? Are you able to draw, to sketch derivative function without even knowing what the original function looks like? You know, on an exam, you don't have the graphing calculator, right? So you get some crazy f of x. You have no clue how to draw that. Well, you will know in 4.3, but for right now, right? For chapter 3, you don't know how to graph, let's say, ln of x squared plus 3, right? Do you know how to graph ln x? Right, probably half of the classroom will be like, and the other half will be like, yes, right? So that's just ln x basic. I'm asking you to graph ln x squared plus 3. So that changes the game, right? We use calculus to figure out all of those things. It's not an issue. But that's in chapter 3. So now, can I sketch a derivative function if I have a curve? I don't know what the function for that curve is, but I know there is a derivative, right? So let's work on that in stages. First, I'm going to start with the absolute value. So f of x is equal to absolute value of x. what is the derivative of absolute value of x? Well, let's think about it graphically rather than compute. If I draw absolute value, it's going to be this V, right, looking shape that goes at 45 degrees forever. We know that we have a slope of the line to be the derivative. So what's the slope of the line here? 1. Because it goes 1 unit up, 1 to the right, 1 up, 1 to the right, 1 right, so it's 1 to 1. So we have to draw the derivative at number 1. How about on the other side? What's the derivative? -1, exactly. There we go. Did we actually take the derivative of absolute value x? No. We just looked at the graph and said slope of the line on the right is +1 always, therefore derivative is constant, it's 1. And then you have the other one on the other side, -1, and that's it. Now, you can actually, looking at the graph, you know it's a piecewise function, you can go and you can construct now the derivative, because you know it's going to be -1 if x is less than 0, and it's going to be +1 if x is bigger than 0. And it's also worth mentioning that you observe two open circles, right? You remember your function definition for the test? It says for every x there is a unique y. You see how there is a struggle? That point exists for the function. I put it in black now, right? This is my f of x. That point at 0 exists for the black function. It cannot exist for the red ones, because you can't have that value to be +1 and -1 at the same time. That would ruin the function, right? We say that this function is not differentiable at 0. Do we have the derivative? Yeah, right here. This is the derivative. You know how function is always continuous unless you have a vertical asymptote or open circle? And then function is piecewise continuous and all of that cool stuff? Well, derivative. See, this particular function has a point that's bad, because that point in the limit from the left wants to be -1 as a derivative, and in the limit from the right wants to be 1. And function doesn't like when you have two values for the same x. So, derivative is a function. We are not allowed to assign that 0 to any of the values. Right? You have to keep that point 0 out in this particular case. And that's that. So that's one of the cool things. We already discussed the 1/x and preserving the vertical asymptote which we had at x equals 0. So keep that in mind. So now, what else can I do? Well, let's now draw an arbitrary function. Actually, no, let's do something predictable first, and then we'll... So let's say that we'll start at the origin, then we'll go 2 units forward, 3 units up, then we're going to go flat 4 units, and then we're going to go 2 units at 45 degrees. Then we're going to go 3 units forward, and then we're going to drop right there. I'll calculate what that is. So we have 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. Okay, good. This is just an arbitrary function. What could this be? Maybe driving, let's say. So you have 15 minutes, right? Time axis here, and then the way you cover the distance or something. It could be anything. This graph could be for anything. Can we draw derivative function looking at this graph? The answer is absolutely yes. Can we draw it precisely? The answer is yes, because all of the values that we need are present on the graph. So what should I do for the first line over here? Where do I draw my red? Y equals how much? Three over 2. Good. So y equals 3 over 2. 3 over 2, that's 1.5. So for this piece, I have this as my derivative. It's 3/2, because that's the slope of that line. What's happening between 2 and 6 minutes? 0. Because it's constant, right? So 2 to 6 is 0. What's happening next one? 1. What's happening next one? 0 again. And how about for the end? It drops down 1, 2, 3, 4, 5, and it goes forward 4. Good effort. Negative 5 over 4, good. That's the derivative. Now, if you're thinking about, let's say, velocity, which we are actually going to have a separate lecture, and the distance covered. So this would be your distance. Let me put blue. So this is your distance, and this is your time. You can see that you are driving, right, with some velocity. Because what is velocity? Velocity is distance over time, right? That's the speed, distance over time. So do you see that for the first, let's say, 2 minutes, you see that you have some change in distance, right? And then what happens here? It's a constant velocity. Actually, maybe I can use, maybe acceleration would be better to understand. What's acceleration? It's a change in velocity, because you can look at your speedometer. So let's do that while we still have time over here. So your speedometer is change of velocity in time. Sorry, that's acceleration. And you have 2 different types of acceleration. You have the gas pedal, which is increase, which is positive, and you have brake, which is decrease, which is negative. So what happens here? If you push the gas pedal, you are getting change in velocity, right, which is positive acceleration. And then if you are not touching brake or pedal, you are going at a constant velocity. So there is no change in acceleration. There's no change in velocity because acceleration is constant. That's what I want to say. So you keep, I'm accelerating, I'm driving constant, acceleration, constant, brake. One more time. Accelerate, constant speed, accelerate, constant speed, brake. So this is my velocity, this is my time, and then the red one is showing us the acceleration, the change. So my initial speed is 0. That's the driveway, right? This is our point of origin. And this is when you park at the parking lot. So you accelerate to get out of the driveway or to the street, and you are already driving at some velocity. So this is now constant speed, and then you accelerate a little bit more because you got onto a highway, right? So, and then now you're not accelerating anymore because now you're on a highway going on a speed, and then now you're at a parking lot here, and you have to decelerate or brake to stop and get the velocity at 0 at the end, because the y-axis measures velocity in this particular example. All of this will be explained again when we have a lecture on it. Might be next week or the following week. It's coming up very quickly. But I needed this example just to show you that, we can figure out the derivative just by looking at the function. We don't have to know what the function is, and it doesn't have to be just constants and linear. So we can have any kind of squiggle. And I'm going to draw a squiggle, and I'm also going to toss in at least one vertical asymptote. So let's say we have that. That was terrible. There we go. And on the other side, we just have this. How about that? So now I want to draw the derivative, and I'll draw that actually on a separate one now. So this is my function, f of x, and this is where I'm going to put my derivative. So it's a y prime on this axis, and it's going to be a red line, right? Well, first off, we learned that we preserve vertical asymptote in the same spot. So this vertical asymptote now, I'm just going to draw this red because it stays in the same spot. Then we said, anytime when you have a min or a max, you are going to get a horizontal tangency, which means tangent line has 0. Well, that's when the derivative is 0. So that means that this is going to cut our x-axis at these locations. So anytime you have a min or a max, that's where the derivative goes through 0. If the graph on top is velocity, when you throw something up, when it gets to its top, it stops. So velocity is 0, right? So the next part is we understand that this part of the graph is a decrease. Then here is the increase. Then there is another decrease. Then there is forever increase. What have we learned from this example and previous ones too? Anytime you have an increase in function, you have increase you have positive derivative. Anytime when you have a decrease in a function, you have negative derivative, negative value. So now I can apply that to this picture. As you can see, between the min and the max, I have increase. If I have increase, that means the derivative is positive. Derivative is positive because of this. And now what I have on the bottom is now decrease. Well, it makes sense that this will pass and follow the asymptote. Do we all see that? Now, what I can't really do well, I don't know how far out this goes. That's the part that I don't know. I need more information for that. But I know for sure that this part goes like this. Because it has to follow the asymptote. It has to be negative on this part because it's decreasing on that part in a regular function. And I also have a decrease to the left of the minimum. That means this. So the decrease in f means f prime is negative. Increase in f means f prime is positive. Another decrease in f means derivative is negative. And finally, over here I have increase. Because I have increase, that means that the derivative will always be positive. Now, it's a little bit tricky here. I have to draw this piece this way rather than this way. Both of these are positive, right? But see, this one kind of wants to cross because you should be following asymptote, right? Asymptote is preserved. I can't have this cross over here because there is no min or a max on that region to make that zero where derivative crosses. So I can't have that. Now, the other one actually makes sense because you have infinite change as you are approaching asymptote, and we are preserving that. But look also what's happening with this particular function. You see how this function is getting lazier over here? Meaning it grows fast here, and again it's getting lazier. You see that? It's getting lazier. If you are measuring the change, we have a rapid change here, which is the rapid change, and then you are kind of approaching the zero change as this goes out forever. Because this is approaching being a constant. That's what it means, being lazier, right? It's approaching constant. If it's approaching constant, then its derivative better approach zero. Does that make any sense? So this is the analysis, right, of functions. And without knowing what the function values are for the black line, I know the sketch of the derivative, which is the red line. Now, do you want to look at the, let's say, a stock value and look at the actual picture, or do you want to take a look at the derivative picture? Which one would give you the health of the stock better. Right? So this is something that is very important to consider, because the answer is derivative. If your derivative of the stock function, right? Well, I'm talking about money and money market, right? Okay, good. So at the stock exchange for companies, right? If you're looking at the derivative, if it's flat, that means no change in value. If it's negative, you're losing money. If it's positive, you're making money. You only need to know whether the derivative is positive, negative, or zero. And you have immediate, right? Now, the bigger the number, the bigger the change. So, if you are losing, right, if it's red, if you're losing, right, that means the larger number means you are losing more money per hour, minute, whatever you want to call it. If it's a larger, if it's a smaller negative number, then you are losing less. If the derivative is zero, no gain, no loss, which is never the case, right? And if you have it in green, you have the value going up in time. I'm going to take a look at the example. Home Depot. I'm serious. We're looking at the stock for Home Depot. Sell, 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 buy, 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 don't touch it. This is not the derivative. This is the original function. This is the fluctuation of the Home Depot stock today. Sell, buy more, or just
Buy.
just look at it.
Just going by the day, buy. That is low.
Yeah, see? That's why you're not making millions on the market, right? You ever look at the day? No, right? Let's take a look at the 5 years. Yeah, well, we can take, yeah. 5 day. 1 month. 6 months. Right? Now, 6 months, 1 day, 6 months. What you do here is you draw the approximate linear line, and what's the slope of that line? It's a positive. The derivative is positive, right? You can't look at 1 day. Now over here we see that the stock went from 178 to 211, right? 178 to 211. 178 to 211. What's the difference? This subtraction is too hard, right? Everyone's looking at us like, huh? What happened? 33, right? So $33. I know. I mean, you did limits. So, like, to ask you a subtraction question, that's blasphemy. So I'm very sorry. You have calculators for that, right? You just ran their batteries out, so you can't do this now, right? You're doomed. The way to compute this thing, right? 211 minus 178. You add 2. But it's much better to add 22, but, well, let's add 22. It's easy. That's the way to, because you want the bottom number to be nice, easy to subtract. So you have 233 minus 200, and it's 33. Right? If a mother gives a birth to a child when she's 33 years old, next year, child is 0. Next year, she's 34, child is 1. In 10 years, she's 43 and child is 10, right? It's always the same difference. So you just add to the bottom number whatever you need to make it nice and flat, and the difference is preserved. So, yeah, that's the fast way to do these things. Anyway, guys, $33 made over 6 months, and if you have 1,000 shares or more, if you have 1,000 shares at $33 is right? So in 6 months with doing nothing, right? You put the money in and you just do this for 8 hours a day, right? If the trend continues, right? That's in a year, and then you tax it, obviously, right? So, yeah, you want a Tesla. Wow. Peace. It's all over the place, right? It's all over the place. But here's the max, right? And max is 6. Oh, why don't you say you can't see it? There's your max at 6 years of what's happening. So it's, year to date. Six months. 1 month. Max. Now you can always follow these, and you have to be really informed, and you can, watch. But the trick is that, what is the derivative, right? And how you deal with this. If you take a look, it's flat, big jump, flat, big jump, flat, right? Makes sense, right? So the derivative over here, it's all positive numbers. I mean, it's 0, 0, 0 when you look at it this way, but there is this jump, right, in value. So you start from 0, going to a stock of 350, 0 to 350 in 6 years on 1,000 shares. That's 350. That's 1/3 of $1 million. So if you bought a stock for Tesla, right? Some of the people who bought Microsoft stock or Google stock or IBM stock where it was nothing, when it was cents. So the business, if you if you have the knowledge and seek out companies that are going public, right, and then buy those shares and hope that in the future they're going to do well. Now it's a gamble, guys. You have to be very informed, and you can buy something at maybe 50 cents or $1 per when it just starts. Companies in Brazil, companies in Indonesia, and so on. I know people that do that. You spend a couple of $1,000s here, a couple of $1,000s there. It just needs to catch on once. You invest $1,000, you have failure like 10 times in a row, but then once, when it catches and does this on a company that deals with oil or a company that deals with pharmaceuticals or something like that, right? And what do? You watch the derivative. You watch the derivative. Positive derivative, making money. Negative derivative, losing money over the time, right? Because the derivative is change in time. Now you have the average change, which is a secant line, and you have instantaneous change. Instantaneous change is the one that you don't want for stocks because when it's changing, right, this is a change in a day, and it seems like that someone who bought the stock 6 years ago for Tesla is losing money, where this drop is, as you can see up there, 69 cents. This person is $350, oh no, sorry, $300. This person is $300 good from being zero in the beginning, right? 6 years ago. And now lost 69 cents per stock today. Sure, maybe tomorrow this is going to be plus $1.50 forward, right? So you have to watch and you have to, always be on top of things. And then if it rides downward trend for a very, and it looks like it's going to hit the bucket, obviously you try to sell it as soon as possible. Good. So this is what we have for the connection between the function, and the derivative. Every vertical asymptote is preserved. When you have increase, derivative is positive above x-axis. When you have decrease, derivative is below x-axis. And when you have min and max, or it's flat, no change, it's 0. And that's it. All of your homework examples are going to be to draw pretty pictures. So go on, draw them. And see you next week.